How do EIGRP routers get specific information from a neighbor? To get specific information on a route, on a network, from a neighbor, EIGRP routers query their neighbors. When a router loses a route and does not have a feasible successor in its topology table, it actively looks for an alternative path to the destination. This is known as going active on a route. So when we say EIGRP goes active on a route, this is what we mean. Two major solutions exist in order to optimize the propagation of these queries. So to optimize the query propagation process in EIGRP, and also to limit the amount of unnecessary EIGRP load on the links, we have two solutions. We use EIGRP summarization to reduce number of queries, or secondly, we use EIGRP stop routing, stop configuration. Implementing EIGRP summarization, it provides several benefits. Not only does it reduce the size of routing tables on the routers, but it also limits the query scope. We know that EIGRP supports both manual summarization as well as automatic summarization, unlike OSPF. With OSPF we only have manual, we don't have automatic summarization with OSPF. Also remember, EIGRP manual summarization is configured on a specific EIGRP interface. So we go under the interface, let's say in this example router 1 interface serial 1/0. If this is the outgoing interface in the routing table for a collection of individual networks that we would like to summarize with one IP, then we go under the interface configuration, we provide IP summary address EIGRP, and then the summary address followed by the summary subnet mask. So 10.1.0.0, 255.255.252.0 in this example. Once again, when connecting to the remote location, it fails and a router has no feasible successor to reach the lost network, it starts by sending query to its neighbors. To reduce queries, we either use route summarization. The neighbor receiving the query will immediately respond with a reply message without further forwarding the query, because it has a summary route and that's it. Secondly, we use stop routing, because we know that non-stop routers, they do not send query messages to stop routers. In this way, we limit the scope for query. A router that is configured as a stop router, it shares information about two types of routes, connected and summary, and that's it. So it shares information about connect and summary routes with all neighboring routers by default. However, non-stop routers, they do not send query messages to stop routers, and in this way we can reduce number of queries in EIGRP by defining the intended routers as EIGRP stop routers. The connected option permits the EIGRP stop router to advertise all connected routes for interfaces that are matched with an EIGRP network command, and is enabled by default and is the most widely practical stop option. The second option that we have here by default enabled is the summary option, and it permits the EIGRP stop router to send summary routes. You can create summary routes once again manually, or you can create them automatically by enabling auto summary at a major network boundary router. No matter which way, neighbor replies immediately to queries with replies. As with summary, there is no need to further forward the queries. Which routes are propagated from the stop router by default? We summarize our discussion and we say that only connected and summary routes are propagated from stop routers by default. A device that is configured as a stop with the EIGRP stop command shares only connected and summary routing information with all neighbor devices by default. Stop routing, the application, you can find it commonly used in a hub and spoke network topology. Different options are available. We can have connected, we can have summary, we can have static, we can have redistributed, and we can have receive only. It's connected, as I said, sends connected routes covered by a network statement, and it's the most widely practical stop option, and it's the default. Summary, it sends summary routes that are created either manually or automatically, and again this is going to be the default behavior. Summary and connected, they are the default. Static stop routes, the stop routers, they can send static routes redistributed from the static using the command redistribute static. Stop routers can be configured to be receive only, meaning that it restricts the stop router from sharing any of its routes with any other EIGRP router. Out of these 5 options, the default one is connected and summary, and that's it. You can have one or more of these 5 in a combination, except for receive only option. So stop routers, they learn routes from non-stop routers, but stop routers do not forward EIGRP learn routes to other neighbors. Only connected and summary will be forwarded, and non-stop routers do not send query messages to stop router. And this is the good news, because in this way we're going to stop propagation of the query messages from non-stop to stop, and we reduce the load of EIGRP traffic on our network. So far we have seen that to get specific information from a neighbor, we send query messages. What if we are not receiving a reply to an outstanding query? When EIGRP returns a stuck inactive or SIA or SIA message, it means that it has not received a reply to a query. If the router does not receive a reply to all the outstanding queries within 3 minutes, this 3 minutes is the default time, then the route goes into SIA or SIA or stuck inactive state. In other words, once the active timer expires, that 3 minutes, the neighbor relationship is reset. That is a bad news. Resetting a neighbor relationships due to a lost reply message is very aggressive behavior in large environments with slower links. It can cause long convergence times and network instability. 2 new additional EIGRP packets were introduced in order to overcome This limitation, the limitation of returning a SIA or stuck inactive message, in order to avoid long convergence and network instability. When no reply to a query is received, EIGRP sends an SIA query packet, SIA query packet, when the active timer is halfway through. So if the active timer is set to 3 minutes or 180 seconds, then that means that the SIA or SIA query timer is 90 seconds, so halfway through. When no reply to a query is received, EIGRP sends an SIA query packet after 90 seconds, and this enables the neighboring router to respond with a SIA reply, SIA reply, and confirm to the upstream router that is still searching for a replacement route for replacing the route that has gone down recently. So SIA query packet and SIA reply packet are two new additional EIGRP packets, and when there is no reply to a query, EIGRP sends SIA query packet halfway through, and the neighbor responds with SIA reply packet to confirm that it is still searching for a replacement route. We have not mentioned so far the reasons for SIA routes to happen. Firstly, the router might be too busy to answer the query, and that makes EIGRP return a SIA message. Another most common reason for SIA routes to happen is the link between two routers that is not good. And the third most common reason is a failure that causes traffic on the link to flow in only one direction. This is called a unidirectional link, and the unidirectional link is the third most common reason for SIA routes. So, three most common reasons for EIGRP to return SIA message, meaning that we have not received a reply to a query. We may have a router that is too busy. We may have a link that is not good, or we may have a unidirectional link. Next stop is load balancing. Remember that EIGRP, unlike OSPF and other routing protocols, is the only routing protocol that is capable of unequal metric load balancing. EIGRP can distribute traffic over multiple links, and this is what we mean by load balancing, leading to the same destination. Traffic can be distributed so that we can increase the effective network bandwidth. Once again, EIGRP supports load balancing over equal metric paths as well as over unequal metric paths. EIGRP enables load balancing between a maximum of 4 equal metric paths, let's say, by default. And this can be done with two different approaches, one with per packet basis approach and another one with per destination based approach. When a packet is process switched, that means that load balancing over equal metric paths can occur on a per packet basis. When packets, however, are fast switched, load balancing over equal metric paths occurs on a per destination basis. Cisco Express Forwarding or CEF switching, enabled by default, can support both per packet as well as per destination load balancing for balancing the traffic over equal metric paths. On the other hand, load balancing over unequal metric links is disabled by default. For unequal metric paths load balancing, it is important that only feasible successor paths can be included in the load balancing. This is to ensure that the topology stays loop-free even when you do load balancing over unequal metric links. The route must be loop-free. This is important. And this condition is satisfied, as you know, when the advertised distance or the metric is less than the total distance, or when the route is a feasible successor, in other words. There is a condition to be met if we want to do unequal metric load balancing. The metric of the route must be lower than the metric of the base route, known by the successor, multiplied by the variance that is configured on the router. So with EIGRP, we already have configured the variance on the router, and its value multiplied by the metric of base route should be greater than the metric of the route that wants to be our additional link. So what you can see is that any feasible successor whose metric is less than or equal to the product of variance by feasible distance is considered equal routes or alternative routes, and that can be placed into the routing table. How many of these routes or equal routes can be considered? Up to the maximum path. So another variable that you need to configure is the maximum path. So variance times successor's metric should be greater than feasible successor's metric. How to check variance value or the maximum path value? These two settings can be verified by using show IP protocols command on Cisco routers. The variance multiplier EIGRP router subcommand defines an integer in the range of 1 through 128, and you can change it. The router then multiplies this variance value by the successor route's feasible distance or successor's metric, i.e. the metric of the base route to reach that subnet. Any feasible successor whose metric is less than or equal to this product, so the product of variance by the feasible distance, are considered to be equal routes and can be placed into the routing table, but up to and including the number of routes defined by the maximum path command. This is for unequal load balancing in EIGRP. Thanks to variance or this integer setting for EIGRP, any feasible successor route whose metric is less than this value multiplier times the successor's metric is added to the routing table within the restriction of the maximum path command. Last point here to consider is the fact that the maximum number of paths varies based on the Cisco iOS versions that you're using or the router platform. However, for the much older iOS versions, we used to have less maximum paths available. So the maximum was 6, let's say, routes. But with later versions of iOS, we can typically have 16 or even more. If you check the maximum metric variance on the show IP protocols, and if you see that it is set to 1, then that means you are restricted to only one path to be used for every network learned. In other words, that simply means that we have disabled the load balancing. Next up is OSPF. OSPF has certain features. We start with the first important feature, that is independent transport. Independent transport means that OSPF works on top of IP directly. That means using port number 89, OSPF does not rely on the function of the transport layer protocols such as TCP or UDP. So it works on top of IP directly. Second important feature of OSPF is efficient use of updates. What we mean is that at very beginning, when an OSPF router first discovers a new neighbor, it sends a full update with all known link state information. So open short path first routing protocol is a link state routing protocol. As soon as it discovers a new neighbor, it sends a full update with all known link state information. All routers at the end of the day within an OSPF area must have identical and synchronized link state information stored in their OSPF link state databases. But the efficient use of updates for OSPF happens later when an OSPF network is in a converged state and later a new link comes up or a link goes down and becomes unavailable. Efficient use of update means that an OSPF router here wants to send only a partial update to all its neighbors. So after convergence happens, then we don't send the full update anymore. We just send partial updates as soon as a new link comes up or an already defined link goes down. This partial update, of course, will then be flooded to all OSPF routers within an area. OSPF operation can be summarized into 5 different steps. The very first step is to establish adjacencies. After adjacencies are established, routers then exchange link state advertisements known as link state advertisements LSA. So after adjacency is established, we exchange LSAs. Second step is to exchange LSAs. LSAs, they contain the state and the cost of each directly connected link. Remember, where to find cost for each link inside LSAs. So LSAs contain the state and the cost of each directly connected link. Routers, they flood their LSAs to adjacent neighbors, and adjacent neighbors in turn, receiving the LSA, immediately flood the LSA to other directly connected neighbors. This happens until all routers in the area have all LSAs. The third step, After the LSAs are received, OSPF enabled routers, they need to build what we know as topology table or linked state database. So OSPF creates topology table based on the received LSAs. Fourthly, routers then execute the algorithm known as shortest path first SPF algorithm. The SPF algorithm creates the SPF tree, and from the SPF tree, fifthly, the best path are inserted into the routing table. And of course, routing decisions now can be made based on the entries in the routing table. These 5 steps explain OSPF operation. OSPF has a hierarchical architecture. It uses a 2-layer area hierarchy. We have backbone area and we have non-backbone area. Backbone area is also called transit area and also called area 0. They are all the same concept but different terms. Backbone area, 2 principal requirements for the backbone area are that first it must connect to all other non-backbone areas, and this area must be always contiguous. What does that mean? It is not allowed to have split up the backbone area. Generally, end users are not found within a backbone area. Second layer of hierarchy is non-backbone area. The primary function of non-backbone area is to connect end users and resources. That's why non-backbone areas are usually set up according to functional or geographic groupings. Traffic between different non-backbone areas must always pass through the backbone area. In multi-area topology of OSPF, we have special commonly used OSPF terms that we need to be aware of. Firstly, ABR or Area Border Router, a router that has interfaces connected to at least 2 different OSPF areas, including the backbone area. ABRs contain linked state database or LSDB information for each area, and ABRs make route calculation for each area and advertise routing information between areas. The second term is ASBR, Autonomous System Boundary Router, or ASBR is a router that has at least one of its interfaces connected to an OSPF area, and the second interface or at least one of its interfaces connected to an external non-OSPF domain. So it can be a BGP domain, for instance. We then have internal router, a router that has all its interfaces connected to only one OSPF area. Finally, we have backbone router, a router that has at least one interface connected to the backbone area. So the name suggests backbone router, a router that has at least one interface connected to the backbone area. It is important for you to know that OSPF is the only routing protocol that we study that only supports manual route summarization. So OSPF is not capable of automatic summarization. You can manually summarize OSPF inter-area routes at ABR, because when I say inter-area, I mean between areas, so it can be ABRs. So manually summarize OSPF inter-area routes at ABR, and you also have the possibility to summarize OSPF external routes at ASPR, because by definition we know that ASPR routers, they sit with one interface connected to OSPF area and at least one of its interfaces connected to an external non-OSPF area. So ABRs and ASPRs are the places to do manual route summarization, and OSPF does not know the concept of auto summarization. For OSPF to operate, we have different OSPF message types. I revise that before I move on to OSPF neighbor adjacency. So OSPF message types start with the famous one, hello packet. So type 1 is hello packet, and hello packets are there to discover, to build, and to maintain OSPF neighbor adjacencies. The second type of OSPF messages is type 2 database description, known as DBD. So DBD packet, we briefly describe our linked state database to our neighbor. When the OSPF neighbor adjacency is already established, a DBD packet is used to describe LSDB or linked state database so that routers can compare whether databases are in sync or not. So I check what I have and what he has, my neighbor. Type 3 message types of OSPF is link state request or LSR. LSR packet, the router will send an LSR packet to inform OSPF neighbors to send the most recent version of the missing LSAs or link state advertisements. In response to LSRs, our neighbor, they send us LSUs or link state updates. So type 4 of OSPF message types is link state update or LSU. LSU packets are used for flooding of link state advertisements or LSAs, and also to send LSA responses to LSR packets. So either initially, at the very beginning, we want to flood LSAs or link state advertisement, and therefore we use LSUs, link state updates. These packets, they can carry link state advertisements. Or later, secondly, in response to specific link state requests, LSRs, we again use LSUs, link state updates, and LSU packets will be sent in response to LSR packets to specify the missing LSAs. And type 5 of OSPF message types or last type is LSAC, link state acknowledgement. LSAC packets or LSACs are used to make flooding of link state advertisements reliable. So we have acknowledgement mechanism in place in order to add reliability here. Whenever we send LSAs, whether it is within LSUs for initial flood of LSAs, or whether this is within LSUs in response to LSRs or link state requests, we need to acknowledge the receipt of LSAs to the sender. This is important to take away that after all descriptions are received in DBD, the neighbors send out database requests, LSRs. for more complete information about the records that were requested. So more complete information means that we initially gave a less explicit, let's say, information about routing in DBD. We described our database, and now with more complete information requested for the records, these requests are followed with a flooding of link state updates, LSUs. And LSUs, they contain the requested information. Think of LSUs as envelopes inside which we have LSAs, link state advertisements, and LSAs is what we are looking for because they contain information about the state as well as the cost of each directly connected link in our network. Next up, we want to see how OSPF neighbor adjacency is established. OSPF enabled interface will pass through several states before becoming adjacent to another router. What these states are is the discussion here. So you can see states are as follow: down, init for initiation, we have two-way, we have X-start, exchange, loading, and full. We are in down state if for more than dead interval OSPF enabled router has not received any OSPF information from anybody. So in down state means that the router has not received any OSPF info for more than the dead interval. We move on to attempt. I don't say it's a different phase, but we categorize it under down state. In attempt state, OSPF enabled router is trying to contact the neighbor by sending unicast hello packets to manually configure neighbor with neighbor command on the interface. This state attempt is possible on non-broadcast multi-access network, also known as NBMA, non-broadcast multi-access. So we are in attempt if we try to contact by sending hello to neighbor. We are in down if we have not received any information. With attempt state, after neighbor command is issued, we send hello, but before receiving hello from the neighbor, we are in attempt state. With down state, however, we have not received any OSPF info from anyone for more than the dead interval. Then we move on to init. Hello received from neighbor. Inside the hello that we have received from the neighbor, we still cannot see our own local router's ID or RID, router ID. Or that might be the case that we have not passed the match checks, because for two OSPF routers to establish adjacency, certain checks needs to be passed, and if we have not passed those checks, we are still in init state. So once again, in init state, OSPF enabled router has received hello from another OSPF enabled device, but the neighbor list of received hello packet does not contain our router ID, does not contain local router ID, which indicates that the neighboring router has not received locally generated hello message from us. That's why he cannot still list our own local RID inside the hello that he has sent to us. That might be the case that this happens. We are in init state because we have not passed the match checks. We then move on to two-way state, similar to init in that we have received a hello from the neighbor, but unlike init, in two-way, inside the hello packet that we have received, we can see our own local router ID or RID. So it has router's ID, and that means the neighbor can see us, and all the verification have passed. That simply means that in two-way state OSPF enable router can plan for the exchange of OSPF database. So once again, two-way state indicates that the OSPF enable router has received hello message from another OSPF enable router or device, and inside the hello packet that was received, the neighbor list of received hello packet contains local router ID, local RID, which indicates that the neighboring router has received locally generated hello message and can see us now. At this state, exchange of OSPF database can start. For routers that are connected to multi-access and non-broadcast multi-access NBMA networks, negotiation will continue from this stage only with designated router and backup designated router only with DR and BDR routers. With DR other routers, well, they remain in two-way. So start exchanging of OSPF database with DR or with BDR, but for those routers that are DR other, those will remain in two-way state. We then move on to access start, where data exchange starting. In XStart state, OSPF enable router, we try to establish initial sequence number. This initial sequence number will be used to synchronize OSPF database. At this state, primary and secondary router will be selected, and the primary router, of course, will poll secondary router. Recall the exchange of DBD packets, database description packets. Here, sequence numbers are used. So negotiating DVD sequence numbers happens in XStart state, and here we specify the master and the slave for starting to exchange the database, linked state database between two routers, between the one that becomes master and the one that becomes slave. Then we move on to exchange. Exchange means exchanging DBD packets, database description packets. Exchange state asks for OSPF enable routers to exchange full database descriptions only. So DBDs only. So DVD exchange happens in exchange state. Then move on to loading. In loading state, OSPF enabled routers will finalize the exchange. And to finalize the exchange, we need to remove all discrepancies. So any discrepancies in the databases will be synchronized with what we know as link state requests, LSRs. Recall that LSRs packets will inform OSPF neighbors to send the most recent version of the missing LSAs. Here, LSR exchanges happens in loading state, and link state updates in response to link state requests will follow. And then we move on to full state. Remember, the final objective is to exchange full link state advertisements for a link state routing protocol. Here, in loading state, this happens thanks to LSRs, LSUs, and of course LSAX. And in this way, we can exchange full LSAs, link state advertisements. And then we have full, and in full state, we are sure that the databases are synchronized. Database synchronization is complete, and the neighboring routers are synchronized and fully adjacent. That means that we have identical linked state databases on all OSPF enabled routers. Routing table calculations can begin, and we can start installing the best route into the routing table and start forwarding packets based on the router's routing tables. I have previously mentioned that there are certain match checks that need to be passed before we move on to two-way state. And if we don't pass those checks, then we remain in the init state. What are those checks for two routers to become OSPF neighbors and establish OSPF adjacencies? Before forming an OSPF adjacency, two routers must agree on these 8 parameters here. They will examine hello packets and check for agreements on the following fields: on hello and dead time intervals. This is very important. If they are different, then the adjacency won't be established. Network type, and I will explain what that means in the context of OSPF later. Network type must match on both routers. MTU must match on both routers to become OSPF adjacent, and both interfaces need to be part of the same subnet. Area ID on both routers must match, and then authentication between two routers must pass, and stop field will be checked and they must match as well. And then the unique router ID needs to be defined on every and each of those routers that want to become OSPF adjacent. So we examine hello packets and we check for agreement on interfaces of each of those two routers in this example to make sure that they are in the same subnet, not configured to be passive. Area must match, hello and dead interval must match, router ID must be unique, authentication must match, and IPMTU value must match. Process ID, however, can be different on two routers when they want to become OSPF neighbors. This is important. Process ID can be different, but those 8 different parameters must match. Next, about OSPF version 3, it was developed to support IPv6 prefixes. OSPF version 3 uses multicast address FF02::5 for all OSPF routers and FF02::6 for all designated routers and backup designated routers, DRs and BDRs. If the underlying network does not have broadcast capabilities, you must establish OSPF neighbor relationships using a unicast address. And if you have to do that, then for IPv6, this address will be a link local IPv6 address. This unicast address will be a link local address. Another important point here, we have talked about LSAs a lot. Here we want to see what link state advertisements include. Information about the state of a router's link is included there. This information includes interfaces, IP address, interfaces, subnet mask, type of network, whether it is Ethernet, broadcast network, or serial point-to-point link. The cost of that link is included inside LSA, and also any neighbor routers on that link will be listed. But in LSAs we don't have information about router ID or area ID or authentication, so it is not about router or the area or the authentication. It is about the link itself, and the most important parameter, the cost of that link. How to calculate cost in OSPF? With Cisco, OSPF uses cumulative bandwidth of outgoing interfaces to calculate cost. For this purpose, OSPF will use a reference bandwidth to calculate the cost for each path. Default reference bandwidth is 10 to the power of 8. That means you put 1 and then 80 in front, 10 to the power of 8, and then divide that by bandwidth. So Cisco iOS OSPF will use bandwidth of the outgoing interfaces to calculate the cost. If left to the default value for the reference bandwidth, then for different interface types we're going to have these costs calculated. For serial interface with 1.5 megabit per second or 1,544,000 bits per second, 10 to the power of 8 divided by this number is going to be 64. For Ethernet interface, we're going to have 10 megabit per second, so 10 million bits per second. So 10 to the power of 8 divided by 10 to the power of 7. The result is 10. So the cost, the OSPF cost for Ethernet interface is going to be 10. For fast Ethernet with 100 megabit per second or 100 million bits per second, we're going to have 10 to the power of 8 divided by 10 to the power of 8, and that means we're going to have the OSPF cost of 1 for fast Ethernet. For gigabit Ethernet, which is 1 billion bits per second or 1,000 million bits per second, we're going to have 10 to the power of 8 divided by 10 to the power of 9, and that simply means that we're going to have again cost of 1, same as OSPF cost for fast Ethernet. For 10 gigabit Ethernet interfaces or 10 billion bits per second or 10,000 million bits per second, we're going to have 10 to the power of 8 divided by 10 to the power of 10, and that means that we want to have again 1 for the cost value. So as you can see, OSPF cost for fast Ethernet, gigabit Ethernet, and even 10 gigabit Ethernet, for all these 3 different interfaces types, we're going to have cost of 1. When there is a gigabit or 10 gigabit interfaces in OSPF domain, for this reason we need to adjust the default reference bandwidth. Next, as I said, one criterion for forming OSPF adjacency and the match checks that happens there is to have a unique router ID. Each OSPF configured router requires a unique OSPF router ID, and for this Cisco has 3 criteria to select the router ID with the most preferred and the highest priority first, that is configured manually, meaning that the router ID is configured manually using the specific command for that. If not, if there is no manual router ID command, then to select the router ID, we select from the highest IP address of any loopback interface configured on that router. And the third and the least preferred is the highest IP address of any physical interfaces. So remember, the interface does not have to be enabled for OSPF. It can be any other physical interface on that router, but we first check for the manual configuration of router ID. If there is no manual router ID command being issued, then we select the highest loopback, highest IP address of any loopback. And the third criterion is the highest IP address of any physical interface, and it doesn't have to be necessarily OSPF interface. Next, we move on to priority. We need to also define the priority to elect designated router and backup designated router. How do we do that? We first need to see what DR and BDR are. As the number of routers on the segment grows, the number of OSPF adjacencies increases exponentially. And remember, with OSPF, every router must synchronize its OSPF database, its link state database, with every other router. And in the case of a large number of routers, this of course leads to inefficiency. For this purpose, on a multi-access segment, the routers that exist on a multi-access segment, they need to elect what we know as a DR or designated router, and also a backup DR or a backup designated router, in order to centralize communications for all the routers connected to that segment. DR and BDR will be used for collection and distribution of link state advertisements on the multi-access segment. So DR and BDR, in this way, they improve network functioning by firstly reducing routing updates and the traffic associated with them. So the DR and the BDR act as a central point of contact for link state information exchange on a multi-access network. Therefore, each router must establish a full adjacency with the DR and the BDR. Secondly, the election of DR and BDR not only reduces the routing update traffic, but also helps better management of link state synchronization, because DR and BDR, they ensure that the other routers on the network, they have the same link state information inside their databases, inside their link state DB about the common segment. So reducing routing update traffic and managing link state synchronization is achieved thanks to DR and BDR election. We need to define priority on routers in order to influence DR and BDR election. The default priority is 1 on all routers. High priority router will win election, and priority 0 here means that we don't want that router to participate in DR-BDR election. So priority 0 will set a router not to participate in election, never become DR-BDR. The router will be DR other. All DR other routers will send their LSAs, link state advertisements, to the DR, and for this purpose they use the address 224.0.0.6. So this multicast address will be used for DR other to contact DR for sending LSAs. Remember, if it is IPv6, this address will be FF02:6 to contact DR and BDR in order to send all the LSAs by DR other. For the link to participate in the link state routing process with OSPF, remember the link itself must be in the up state. You can't expect a link that is down to participate in OSPF. So no shutdown command needs to be issued there firstly. And of course, for OSPF, that link or that interface also needs to be included in one of the network statements. In broadcast and non-broadcast multi-access network, there will be election for designated router or backup designated router. DR and BDR. DR will be used for collection and distribution of LSAs. For election of DR, following criteria is used. DR will be the router with the highest interface priority. Remember, the default value for interface priority in OSPF is 1, and then BDR will be the router with the second highest interface priority. So the first highest one goes with DR and the second highest one goes with BDR. If priority is left to the default value, that is 1, then the router with the highest router ID will become designated router, and the router with the second highest router ID will become BDR. I already explained the highest router ID, how it is selected. All other routers will then become DR other. This is important. Multi-access segment elects DR and BDR in order to centralize OSPF communication for all routers connected to the multi-access segment. That means only LSAs are sent to DR and BDR. It doesn't mean that the DR and the BDR are here to do the normal routing. Normal routing takes place with all routers. But for decision making, routing decision making, LSAs and only LSAs are sent to DR and BDR. DR performs LSA forwarding and link state database synchronization. On the multi-access segment, it is normal behavior that the router in DR other status is fully adjacent with DR and BDR. So if you go back to the states, it becomes fully adjacent with DR and BDR. But for routers with DR other status, they all remain in two-way OSPF state. Router in DR other status is fully adjacent with DR and BDR and in two-way state with all other DR routers on the segment. Why two-way? Because once OSPF neighbors are in two-way state, the DR and BDR election process begins, and that is required if the current DR and BDR fail and we need to enforce election. For this purpose, router in DR other remains in two-way state with all other DR other routers. Every broadcast and non-broadcast multi-access or NBMA OSPF enabled interface is assigned a priority, as I said, and the value for priority can be from 0 all the way up to 255. But the default, as I said, is the OSPF interface priority of 1. Of course, this can be manually changed by using the IP OSPF priority interface command. And if OSPF interface priority is 1 for all routers in multi-access network type, then in order to break the tie and elect the designated router DR and backup designated router BDR, highest priority is not enough, and that's why we use highest router ID to break the tie. If they are not all set to the default of 1, then to determine DR and BDR, OSPF will look at priority value, and the higher value the better, or the more preferred. But once again, the default priority for broadcast and non-broadcast OSPF network type is 1. What if we set priority to 0? If priority is 0 on broadcast or non-broadcast OSPF network type for a router, then that means that router will not participate in OSPF election for DR and BDR. So if you are sure that you don't want a router to participate in the election, then just set the priority for that router to 0. What about point-to-point and point-to-multipoint network types? Because there is no need for DR and BDR election in point-to-point or point-to-multipoint network types, then the default priority can be set to 0, and that means that this attribute will not be used. That's why if under state values you check with Cisco iOS, you see that for point-to-point or point-to-multipoint network types, you see the status as full/hyphen. And hyphen here means that there is no need for DR or BDR election. Next up is OSPF network types. 6 different network types are defined here. First one is loopback. In loopback OSPF network type, that is usually used in test lab environments, there is no need for DR or BDR election. This behavior is very similar to point-to-point and point-to-multipoint network types. So loopback point-to-point and point-to-multipoint, there is no need for election. In point-to-point OSPF network type, routers use multicast address in order to discover neighbors, and there is no DR or BDR election. And again, if you check the state, you see that it is represented with hyphen or dash under state, and that means that there is no election needed. Point-to-point OSPF network type is the default for serial links. So if you have serial connections, if you check the status, you see hyphen for DR or BDR election. Also, point-to-point OSPF network type is default for the frame relay point-to-point sub-interfaces. Just to recap, there is no need for DR or BDR election in point-to-point, point-to-multipoint, and that's why the default priority is set to 0, and that attribute will not be used. In broadcast OSPF network type, however, routers not only use multicast address in order to discover neighbors, but also there will be election for DR and BDR. Recall that DR will be used for collection and distribution of link state advertisements. Also, very important to remember that the broadcast OSPF network type is the default for Ethernet links. So far we have seen the default for serial and frame relay point-to-point sub-interfaces is point-to-point OSPF network type, and now we see that for Ethernet connections, the default OSPF network type is broadcast. Fourth type of OSPF network types is NBMA, So in non-broadcast OSPF network type, routers are connected without broadcast capability or multicast ability, and that simply means that neighbors must be configured statically, and there will be election for DR and BDR, so that DR and BDR will be used for collection and distribution of link state advertisements. When there is no broadcasting and no multicasting, that means that there is no dynamic discovery of neighbors, and that simply means that we need to define neighbors statically with NBMA networks. In fact, OSPF treats NBMA as broadcast network type. So similar to broadcast network type, NBMA needs to have DR and BDR election. However, unlike broadcast, here we need to define neighbors statically. NBMA network type for OSPF is the default for all physical interfaces and multi-point sub-interfaces using frame relay encapsulation. So if we have frame relay encapsulation for multi-point sub-interfaces and also for all physical interfaces, then NBMA network type is the default for OSPF. One variant of this is NBMA hub and spoke architecture that is built using PVC and SVC. In this specific architecture, we're going to have a hub as designated router, and spokes, they act as DR other. For this purpose, the priority on spokes need to be set to 0, so that spokes, they don't participate in election, because we want to enforce the hub to become and to remain as DR. Fifth category is point to multipoint OSPF network type. Routers use multicast addresses in order to discover neighbors, and there is no need for DR and BDR election. As there is no need for DR and BDR election in point-to-point and also in point-to-multipoint, that means the default priority is set to 0 and that attribute will not be used. In fact, OSPF treats point-to-multipoint network type as a collection of point-to-point network type, and that simply means that we're going to have multicast to dynamically discover neighbors, and similar to point-to-point, in point-to-multipoint we don't have DR and BDR election. The sixth category is the Cisco proprietary architecture. We have point-to-multipoint non-broadcast OSPF network type. This network type is the same as point-to-multipoint, and the exception is that there is no dynamically discovery of neighbors. In fact, neighbors with Cisco point-to-multipoint non-broadcast network type are defined statically using unicast communication, and there is no need for DR and BDR election. So we have seen so far that we are using multicast here in order to dynamically discover neighbors. We have seen non-broadcast multi-access networks that they don't have broadcast or multicast ability. They need neighbors to be defined statically using unicast communications. And we have seen that the election of DR and BDR only happens on non-broadcast multi-access and also broadcast multi-access networks. We also have seen that the default network type for serial links is point-to-point. For frame relay point-to-point sub-interfaces is point-to-point network type. For Ethernet links, the default OSPF network type is broadcast. And for all physical interfaces and also multi-point sub-interfaces with frame relay, the default network type is NBMA. Just to recap, in loopback OSPF network type is usually used in test lab environment. There is no need for election. In point-to-point, we have routers that are using multicast addresses in order to discover neighbors, and again there is no DR or BDR election. Broadcast OSPF network type, routers use multicast address to discover neighbors, and there will be election, and DR will be used for collection and distribution of LSAs. In non-broadcast OSPF network types, routers are connected without broadcast or multicast ability, and therefore neighbors must be configured statically, and there will be election, of course, so that DR and BDR can be used for collection and distribution of LSAs. In point to multi-point OSPF network type, routers use multicast addresses to discover neighbors, and no election will take place. Recall that OSPF treats point to multi-point as a collection of point-to-point network type. So routers use multicast and there is no election. We have Cisco point-to-multi-point non-broadcast OSPF network type. And non-broadcast here, it means that it must be configured statically for the neighboring routers, and unicast communication needs to be used, and of course there is no election. So to summarize, we use multicast for neighbor discovery, dynamically discovering the neighbors, and multicast is used with point-to-point, point-to-multipoint, and broadcast network types for OSPF. Which OSPF network types need to elect DR and BDR? Election happens only on broadcast and also non-broadcast multi-access networks. Broadcast and non-broadcast multi-access network, there will be election. Next up is LSA types. LSAs are messages inside LSUs. As I said, LSUs, they are like envelopes, and inside envelopes we have letters, and letters here are LSAs. We have different LSA types and we need to remember them. Type 1 LSA is called OSPF router LSA. Every router generates type 1. Type 1 router LSAs are flooded only within the area, so not between area. They do not leave the current area. The purpose of type 1 OSPF router LSA is to describe state of the router links. And when I say state of the router links, you can think of link state information, IP, mask, network type, whether it is Ethernet or serial. The cost, very important for SPF algorithm, and any neighbor on that link, they will be described in type 1 router LSA. While every router in the network generates type 1 LSA, type 2 LSA called network LSA are only generated by designated routers for multi-access networks. So type 2 LSA or type 2 network LSA is for describing routers attached to multi-access network and therefore are generated by designated routers. Similar to type 1, type 2 network LSAs are only flooded within the area and therefore they do not leave the current area. In addition to describing routers attached to multi-access network with type 2 network LSA, also we advertise the IP interface address of the designated router to all routers in the multi-access or non-broadcast multi-access NBMA network. Network LSAs type 2 are flooded only within the area once again, and all routers within the area will have a record about LSA type 2 or network LSA in their databases. Even for the network types that do not use LSA type 2 or network LSA, they still receive it. How do we specify the IP address for designated router? Well, let's go back to where we discussed the OSPF message format. We know that OSPF sits directly on top of IP. So we're going to have IP header plus OSPF message. OSPF message itself consists of OSPF message header plus body of the OSPF message. And inside body of OSPF message, we're going to have message type specific data plus a collection of LSAs. And for each of those LSAs, we're going to have LSA header plus LSA data. For all types of LSAs, there are 20 byte LSA headers. One of the fields of the LSA header is the link state ID. And this link state ID field is very important because the link state ID for LSA type 1 router LSA is the originating router ID, so that we know which router has generated this router LSA or type 1 OSPF router LSA to describe the state of the router links, including the IP, network type, cost, and any other neighbor on that link. Similarly, the link state ID of the type 2 network LSA is the IP interface address for designated router. The link state ID therefore is very important, and in different LSA types it pinpoints to a specific information. Next, we know that there is no auto summarization by default in OSPF. We only have manual summarization, whereby with ABR we summarize one area for another. For this purpose, OSPF type 3 summary LSA is used. Type 3 generated by ABR, always remember. They represent networks from an area and are sent to the rest of the areas in OSPF domain. Type 1 and also Type 2 LSAs do not cross area boundary. So Area Border Router ABR uses Type 3 LSA in order to inform other areas about networks learned in its area. So back to the format and structure for OSPF message. The link state ID of the Type 3 LSA is the destination network number. We then move on to OSPF Type 4 LSA and OSPF Type 5 LSA. These two come together. I first explain Type 5 LSA, known as Autonomous System External LSA. So Type 5 AS External LSA. Type 5 AS External LSA is used for advertising external links to the OSPF domain. Type 5 AS External LSAs are generated by Autonomous System Boundary Routers or ASBRs in order to describe routes to destinations that are external to the autonomous system, and therefore they are non-OSPF domains. Type 5 AS External LSAs are flooded everywhere except into the special areas. And we know special areas as stub areas, totally stub areas, not so stubby areas, and totally not so stubby areas, NSSA and totally NSSA. These four are special areas, and type 5 external AS, external LSA are not flooded there. For this purpose, for LSA type 5 AS external LSA to work, we need type 4 ASBR summary LSA to tell us simply how to get to ASBR and through ASBR to the external non-OSPF domain. So type 4 ASBR summary LSA informs the rest of the domain, OSPF domain, how to get to ASBR. For this purpose, we need ABRs to generate type 4 ASBR summary LSAs. So remember, type 4 ASBR summary LSAs are generated by ABRs. Also, it is important to remember that type 4 ASBR summary LSAs use the link state ID for the router ID of the described ASBR. Once again, the link state ID within the 20-byte LSA header is used to pinpoint the ASBR in this case with type 4 here. The link state ID of the type 5 LSA is the external network number. This is important to know the difference between type 4 and type 5. So once again, which OSPF router type will generate LSA type 4 or OSPF ASBR summary LSA? Link state advertisement type 4 or OSPF ASBR summary LSA are generated by area border router ABRs. It describes type 4. It describes reachability to ASBR, Autonomous System Boundary Router. In the area where Autonomous System Boundary Router or ASBR is located, ASBR will identify itself as ASBR with external bit or E-bit set. ABR then will inform routers on the other areas with LSA type 4 on how to reach ASBR. This is important. OSPF routers will learn external routes to the current OSPF domain thanks to LSA type 5 or Autonomous System External LSA. And OSPF router will learn about external routes thanks to type 5 with the ASBR's router ID. So with type 5, the AS external LSA, the LSA itself just mentions the ASBR's router ID, but how to get there? They will have no idea how to reach ASBR until we have LSA type 4 to inform how to reach ASBR through the router that generates LSA type 4, which is ABR. LSA type 4 are not forwarded to special areas like stub, totally stubby networks, not so stubby, and totally not so stubby. They don't receive type 4 nor type 5. Special area like stub area, they will receive local area LSAs. So type 1, type 2, and type 3 with stub area, and only type 1 and type 2 with totally stub area. Stub area therefore allows LSA type 3 summary LSA for inter-area summarization, address summarization, or network summarization. Stub area, once again, similar to totally stubby area, similar to not so stubby area, and similar to totally not so stubby area. They block external LSA, so AS external LSA type 5, and if there is no type 5, there is no need for LSA type 4. So these four special areas, they block LSA type 4 as well as LSA type 5. Hopefully we have another LSA called type 7 to be used in a special area for not so stubby area. Again, we don't have LSA type 4 and LSA type 5 in not so stubby area as you expect, but we have type 7 NSSA LSA to be used for external routes to be advertised to not so stubby area. This is type 7 LSA. Two more LSA types, type 8 and type 9. LSA type 8 and LSA type 9 both are used in OSPF version 3 for IPv6. LSA type 8 for OSPF version 3 is used for linked local addresses of IPv6 dissemination. Type 9 LSA used in OSPF version 3 for IPv6 for intra-area prefix dissemination. Finally, to recap, for special areas with stub area, LSA type 1, 2, 3 are allowed. With totally stub area, only LSA type 1 and 2 are allowed. Therefore, for transition from stub to totally stub, we block type 3 summary LSA. Then we have not so stub area, and we allow type 1, type 2, type 3, and also type 7 for special area NSSA for external routes, and for transition from NSSA to totally NSSA, we block type 3 or summary LSA, and therefore we only allow LSA types 1, 2, and 7. Next stop is BGP, Border Gateway Protocol, the de facto interdomain routing protocol in the internet today, the protocol that facilitates the spread of network layer reachability information between ISPs and autonomous systems behind them. This protocol was designed very simple to scale for the scalability reason, and of course BGP that for this reason does not care about security much. BGP is an old protocol, but it is still in use because of the massive deployment in the production environment. The main goal of BGP is to provide an interdomain routing system that guarantees the loop-free exchange of routing information between autonomous systems, ASS, BGP routers exchange information about paths to destination networks. This protocol is known as path vector routing protocol. Some say that it is an advanced distance vector routing protocol, but this is not quite accurate. It's better to be known as a path vector routing protocol. BGP is usually based on a set of policies and not just the technical characteristics of the underlying infrastructure like what we had with interior gateway routing protocol. With EIGRP, exterior gateway protocols, and the main one here, the focus BGP, we have two different facets. We have the technical characteristics, and the second dimension is the policies implemented between neighboring ASs. So exterior gateway protocol, here BGP, disseminates network layer reachability information, basically prefixes and their masks between autonomous systems. The policies for BGP are based on the attributes carried in the routing information and configured on the routers. There are 4 BGP attribute types. This is important. Well-known mandatory category, well-known discretionary, optional transitive, and optional non-transitive. The famous, well-known mandatory BGP attributes are origin, autonomous system path, and next hop. And when I say well-known mandatory attributes, that means that these attributes, they have to exist in the BGP update and they must be recognized by all BGP speakers. If we can't see them as BGP speakers, if we can't see them, then we provide notification error message because it has to be there. So 3 well-known mandatory BGP attributes that we have seen are origin, AS path, and next hop. Well-known discretionary, very famous example is local preference, and of course automatic aggregate. Optional transitive aggregator, an example of that. And optional non-transitive, the famous example is MED. Also community originator ID or cluster list. These are all different BGP attributes categorized under non-transitive, optional non-transitive type of BGP attributes. So because of these attributes, we are saying that BGP is a path vector routing protocol. The path vector information includes a list of the full path of BGP autonomous system numbers in a hop-by-hop manner. And this full path is necessary to reach a destination network, because through this path, thanks to AS path attribute, we know how to reach a destination network. This is the AS path attribute. Other attributes that I just mentioned include the IP address to get to the next autonomous system, known as next hop attribute, and categorized under well-known mandatory BGP attribute type. Also, origin is another example for well-known mandatory attribute type that tells us how the networks at the end of the path were introduced into BGP. For this, we use the origin code attribute. So origin, AS path, and next hop, in other words, well-known attributes, are the one that all BGP implementation must recognize and propagate to their neighbors. So this is important. In fact, well-known attributes, no matter if it's mandatory or discretionary, should be recognized by all BGP speakers because it is well known, as the name suggests. With well-known mandatory, the attribute must appear in all BGP update messages, With well-known discretionary, the attribute does not have to be present in all BGP update messages, but must be recognizable by all BGP speakers. So if you receive a BGP update without a specific local preference value inside BGP attributes, it is still acceptable because it does not have to be present in all BGP update messages. But you, as a BGP speaker, must recognize what local preference is. How about optional attributes? BGP routers that implement an optional attribute might propagate it to other BGP neighbors, but it depends on its meaning. So that's why we have optional attributes. Two types: transitive, non-transitive. Optional transitive, that means that BGP routers that do not implement an optional transitive attribute should pass it to other BGP routers untouched and mark the attribute as partial. So remember, only optional transitive attributes might be marked as partial. We don't have such concept partial for non-transitive. We only have that for transitive. Optional non-transitive, on the other hand, this implies that BGP routers that do not implement an optional non-transitive attribute must delete the attribute and must not pass it to other BGP routers. So in short, we have mandatory, discretionary, transitive, non-transitive. Well-known mandatory must appear in all BGP updates. Discretionary not have to be present in all. Transitive, if you do not implement, then it should be passed untouched. Non-transitive, if you do not implement, you must delete and must not pass it. Next, let's see some characteristics of BGP as a path vector routing protocol. First, as you can see from the figure towards the bottom of this slide, BGP operates over TCP. So to recap, OSPF and EIGRP reside directly above IP. RIP, Routing Information Protocol, uses UDP, User Datagram Protocol. However, BGP is the only IP routing protocol to use TCP. Each autonomous system advertises to the neighboring autonomous system, or AS, only its best path, the same way that interior gateway protocols announce only their best, least metric routes. So again, with BGP, only the best path will be advertised to neighbor. After the TCP connection is made, the routers exchange their full BGP tables first. We see different tables shortly, but for now, remember, as soon as TCP connection is up and running, the routers exchange their full BGP tables. However, because the connection is TCP based, in other words, the connection is reliable, BGP routers need to send only changes after that point. That's why we say after full BGP tables exchange, we're going to only have incremental updates or triggered updates after that, meaning that we only send changes. Periodic routing updates are not required on a TCP or a reliable based link. You don't need to send updates periodically over a TCP or a reliable link. That's why with BGP we use incremental updates or triggered updates whenever there is a change, we send an update. Otherwise, we don't need to send anything. This triggered or incremental updates is doable thanks to using TCP by BGP. As I said, BGP is the only IP routing protocol to use TCP as its transport layer. OSPF and EIGRP, they both reside on IP directly, so directly above IP, and RIP uses UDP for transport, and that means OSPF and EIGRP, they need to have their own internal functions to ensure that the update or the updates are explicitly acknowledged. With BGP, we don't need to care about that because we know that TCP is already taking care of that. EIGRP and OSPF, these protocols, for this acknowledgement mechanism to become reliable, meaning that when we send an update, we make sure that the recipient has received the update. For this purpose, they use a 1-for-1 window, so that if either OSPF or EIGRP has multiple packets to send, the next packet cannot be sent until an acknowledgement from the first update packet is received first. This process can be very inefficient and can cause latency issues if thousands of update packets must be exchanged over relatively slow serial links. The good news, however, was that OSPF and EIGRP rarely had thousands of update packets to send. EIGRP, for instance, can hold more than 100 networks in one EIGRP update packet. That means if we have 100 EIGRP update packets, it can hold up to 10,000 networks, 100 times 100. And most organizations, we know that they do not have 10,000 subnets. So that mechanism works fine and fits with interior gateway routing protocols. But with exterior one, well, BGP has many more networks on the internet, and in particular the core of the internet, to advertise. 2014, many years ago, it was 500,000 of subnets and prefixes to advertise. You can imagine that now how much it would be. It uses TCP to handle the acknowledgement function for this reason, because of the very high number of prefixes to advertise. We cannot use 1-for-1 window for acknowledgement system. TCP uses a dynamic window, unlike what we had with EIGRP and OSPF for 1-for-1 window. Here we're using dynamic window thanks to TCP, which allows up to 65,000 bytes, or 65,576 to be precise, to be outstanding before it stops and waits for an acknowledgement. Simply, if we have 100 byte packets to be sent and the maximum window size is being used, that means BGP would have to stop and wait for acknowledgement of only 650 packets had not been acknowledged. Or if we increase the size of packets, let's say we have 1000 byte packets are being sent and the maximum window size again being used, BGP would have to stop and wait for an acknowledgement only if 65 packets had not been acknowledged. So you see how this mechanism is more efficient and reduces the latency. TCP, in addition to the dynamic window, has this characteristic for its window that is called a sliding window. So it is designed to use a sliding window where the receiver sends an acknowledgement before the number of octets specified by the window have been received. Let's say in halfway point of the sending window, we send acknowledgement. This method allows any TCP application, and in our case here BGP, to continue streaming packets without having to stop and wait, as OSPF or EIGRP would require. Next, I want to talk about 3 different BGP tables. Remember, these 3 are BGP tables, and if you consider the main router's routing table, together they're going to be 4 different tables in the context of BGP. For BGP routing tables, 3 types of tables include adjacency RIP in or adjacency routing information base in. Second one is adjacency RIP out or adjacency routing information base out. And the third type is local RIP or local routing information base. And the main routing table of the router, that's the 4th one, of course. But for BGP tables, we have these 3. Adjacency RIP in stores the unprocessed information that you receive from your BGP peers, or in other words, from your BGP neighbors. Then we apply policies, and that means that path is entered into the local BGP table, i.e. local RIP. From local RIP table, next hop address of the route, BGP route, is checked to see if it's reachable by IGP, Interior Gateway Protocol. And provided that it has the lowest administrative distance for that network, meaning that we have not heard about that network by any other sources of routing with a better administrative distance, i.e. lower administrative distance, and this current BGP one is the best one, then that means that we're going to introduce this path or enter this path into the main routing table. And a copy will go also to the adjacency RIP out, meaning that the best BGP path will be advertised to our neighbors or other BGP peers. So I would summarize that in 4 different steps. Firstly, prefix received by multiple neighbors and peers are stored in adjacency RIP in. Policy is secondly consulted and implemented, and then the path is stored in local RIP or the BGP table. Thirdly, the BGP path selection process happens, and then selection process picks only one best path, and that one best path is passed to the router's routing table if no other entry in the routing table with a lower administrative distance for that network exists. Fourthly, one best path is also passed to the adjacency RIP out table to be advertised to our BGP peers. Why we need different tables? Because we may have our inbound policies different from our outbound policies. So because of the inbound policies that may be different from the outbound policies, we need 3 different tables for BGP with adjacency rib in unprocessed routing information received from our neighbors are stored without applying any filtering or without any attribute manipulation. But there might be some filtering or some policies or some manipulation of BGP attributes in place for the inbound updates for BGP that we receive, and for that reason we have our second BGP table, that is the BGP table or local RIB best routes selected after routing policies on the routes available in adjacency RIB in are applied. So after applying routing policies on the routes available in adjacency RIB in, best routes are selected and delivered to local RIB or the BGP table. We also need another table, the third table, adjacency RIB out, to implement our outbound policies. So routes selected from local RIB or BGP table after applying outbound routing policies are then summarized in one best BGP route to be delivered in update to other BGP neighbors that we have, those who want to hear from us, because this is a hop by hop paradigm. This is a hop by hop routing protocol known as a hearsay routing protocol. One whispers something into our ears, we need in turn to whisper that into the ear of the person sitting next to us. 3 different show commands to see these 3 different BGP tables. Remember, show IP BGP neighbor A.B.B, A.B.C.D advertise routes, tells you about adjacency RIB out. Show IP BGP displays the local routing information base or local RIB or BGP table to you, and then show IP BGP neighbor A.B.C.D received routes displays the adjacency RIB in information. To wrap up our discussion so far, we have seen BGP routing process. It starts from establishing adjacency explicitly configured for each neighbor by neighbor command. So later we start periodically sending BGP and TCP keep alives to make sure that the connection is up and running, the adjacency is up and running with our next BGP neighbor. We then exchange best BGP routes that we are aware of, and then the neighbor collects them and places them all in BGP table and selects the single best route for each network by route selection process that we will see later using the BGP attributes. Each router then is going to offer the best route to IP routing table, and best route is going to be installed in that routing table provided that the administrative distance is lower than any other routing source hearing about that network and advertising about that network. No matter if it is being installed in the main routing table or not, best BGP route will still be propagated to other BGP speakers thanks to adjacency RIB out table. BGP routes do not have outgoing interface in the routing table, but only the next hop IP is shown there, and this next hop IP is the IP that is known through next hop attribute of BGP update message. Therefore, a recursive lookup will be done in the routing table, and unlike some other routing protocols, BGP does not require periodic refresh of the entire routing information base, or RIP. This is because instead of that mechanism, BGP routers store the latest version of the routing table of each equal neighbor. So they work based on the version. Although BGP keeps the routes of all possible paths to any particular network, it advertises only best routes in the update message. As I said that before, only best optimal routes are advertised in updates. Network command in BGP, this is important, there is a very subtle difference here. Network command works in a completely different way in BGP than it does in the IGP protocols, interior gateway protocols. In the context of BGP, network command specifies what network to announce rather than what interfaces to run the protocol on, as it was the case in IGP. The network command in BGP context is simply telling this prefix, and therefore that prefix needs to be taken from the local RIP table or from BGP table. Therefore, you can see that BGP stability is very much dependent on the routing tables and consequently on the interior gateway protocol. Because when we say network A.B.C.D inside BGP, we need to have a route, a valid route to that subnet in our routing table. And you see how interior gateway routing protocol may come to help with this regard.